Deputy Executive Information Engineers in Andhra Pradesh Information Services, Electronics and Communication Engineering, 2019 Question Paper Solutions Part 1, that is from question number 1 to question number 30. First question, while increasing the device temperature, the sub-threshold source to drain leakage current of MOSFET will be increased. As temperature increases, the intrinsic carrier concentration in MOSFET increases, which leads to increase in sub-threshold leakage current, and the increase is exponential. This sub-threshold leakage current increases exponentially with increase in temperature. Correct answer is option 1. Second question, the voltage standing wave ratio is calculated by. So we need to identify the correct formula. So we know that voltage standing wave ratio is VSWR is equal to 1 plus mod gamma by 1 minus mod gamma. Correct answer is option 4. Voltage standing wave ratio lies between 1 to infinity. The range of VSWR is 1 to infinity. Next question. The inverse Z transform of the function x of z is equal to log of 1 by 1 minus a inverse z, and the region of convergence given is mod z less than a. We know that log of 1 by 1 minus x is equal to sigma m is equal to 1 to infinity x power m by m mod x less than 1. So using this formula, try to expand the given function. Here x is equal to a inverse z for mod x less than 1, mod of a inverse z less than 1. So we will get mod z less than mod a. So we will get x is equal to a inverse z whole power m, that is 1 by m a power minus m z power m. Apply z transform formula. X of z is equal to sigma n is equal to 1 to infinity x of m z power minus n. So here z is plus m z power plus m, here z is z power minus m in the z transform. So replace m is equal to minus n for a left sided signal. Then we will get x of n is equal to minus 1 by n a power n u of minus n minus 1 for a left sided signal. Therefore correct answer is option 1. Question number 4, match the group A items with group B. So in group A they have given LED, light emitting diode, laser, light amplification by stimulated emission of radiation, avalanche diode and tunnel diode. So we know that tunnel diode is very heavily doped diode. So normally the doping in PN junction diode is 1 impurity atom per 10 power 8 atoms per centimeter cube. The doping in GNOT diode is 1 impurity atom per 10 power 5 atoms per centimeter cube. The doping in tunnel diode is 1 in 10 power 3, 1 impurity atom for 10 power 3 atoms. Therefore tunnel diode is a heavily doped PN junction diode. Tunnel diode is very heavily doped PN junction diode. The tunnel diode electric current decreases as applied voltage increases. Next, avalanche diode. So internal current gain is possible in avalanche diode. LED, in light emitting diode, spontaneous emission exists, whereas in case of lasers, stimulated emission exists. So these are the graphs showing spontaneous emission, and here B indicates spontaneous emission and C indicates stimulated emission. So LED is spontaneous emission and laser is coherent radiation. So correct answer is option 3, 1C, 2D, 3A, 4B. Next question, switching regulator has dash efficiency. The efficiency of switching regulators is very high. The switching regulators like buck boost buck boost converters are known for their very high efficiency, typically in the range of 80 to 90% or even higher. Correct answer is option 2, very high efficiency. Question number 6, it is related to stability factor. We know that stability factor is a measure of how well a transistor circuit maintains its operating point or quiescent point despite of changes in temperature. A low stability factor indicates better stability, that is, circuit operating point is less affected by variations in ICBO, collector base leakage current, as well as beta and VBE. Ideally, the stability factor should be perfectly zero to keep operating point stable. Practically, stability factor should be minimum as possible. The thermal stability of circuit can be assessed by using the stability factor S. The stability factor indicates the degree of change of operating point due to variation in temperature. So stability factor is rate of change of collector current with respect to collector leakage current, keeping VBE and beta constant. Or stability factor S dash is rate of change of collector current with respect to VBE, keeping IC1 beta constant. One more definition, S double dash is rate of change of collector current with respect to beta, keeping IC1 VBE constant. So these are the three different formulas for to calculate the stability from the given options. It is rate of change of collector current with respect to ICO leakage current, keeping VBE and beta constant. Correct answer is option 4. Question number 7. How might a square wave be generated from a triangular signal? So input is triangular signal, we need to generate a square wave. So by using comparator circuit, for a comparator circuit, if input is triangular wave, the output will be square signal. So pass the triangular wave into a comparator to produce a square wave. So correct answer is option 2. Pass the output of triangular wave generator into a comparator to generate a square signal. Question number 8. Despite the presence of negative feedback control system, still have problems of instability because despite the presence of negative feedback in control system, still have the problems of instability because components used in the control system have non-linearity. Despite the presence of negative feedback, control systems still have the problems of instability because the components used have non-linearity. There is always some variation compared to ideal characteristics. Question number 9. Among the basic processes in order to use in silicon planar technology. Question number 9. Arrange the basic process in order to use in silicon planar. Question number 9. Arrange the basic processes in order to use in the silicon planar technology. So it is initially substrate preparation, epitaxial growth, SiO2 growth, photolithography, diffusion and metallization. So the order of processes used in silicon planar technology in IC fabrication are, so first is crystal growth and wafer preparation, that is substrate preparation, oxidation, epitaxial growth and SiO2 growth, photolithography, diffusion or ion implantation, metallization, passivation and packing. So correct answer is option 3. Substrate preparation, epitaxial growth, SiO2 growth, photolithography, diffusion, metallization. Next question. A super heterodyne receiver is to operate in the frequency range of 550 kHz to 1650 kHz with intermediate frequency of 450 kHz. Let R is equal to C minimum to C maximum denote the required capacitance ratio of local oscillator, and IF represents the image frequency in kilohertz of the incoming signal. If the receiver is tuned to 700 kHz, then we need to calculate the value of R and IF. So given intermediate frequency IF is 450 kHz and the incoming signal frequency is 700 Hz, because the receiver is tuned to 700 kHz. We need to calculate the image frequency IF. So image frequency is incoming signal frequency, that is 700 kilo plus 2 times of intermediate signal frequency 450 kHz, that is 700 plus 900 1600 kHz is a incoming signal frequency. 1600 kHz, option C and D. There are two options. Then we need to calculate the value of R, the ratio of C minimum to C maximum. For that, in the question, the carrier frequency range is from 550 kHz to 1650 kHz. So given the carrier frequency range is from 550 kHz to 1650 kHz, local oscillator frequency, the formula for local oscillator frequency FL is equal to Fs plus intermediate signal frequency. Now, if incoming signal frequency is, first case, if incoming signal frequency is 550 kHz, then local oscillator frequency FL is equal to 550 plus FIF. Intermediate frequency is 450 kilo. So that is FL1 is 550 plus 450, 1000 kilohertz. Second case, if incoming signal frequency Fs2 is maximum 1650 kilohertz, then local oscillator frequency FL2 is Fs2 plus intermediate frequency 450, its value is 2100 kilohertz. Now we need to calculate the value of R, that is C minimum to C maximum. So capacitance is, we know that frequency is inversely proportional to capacitance. Frequency is inversely proportional to capacitance. So capacitance minimum is frequency maximum. So that is 2100 by 1000 kilohertz whole square. Its value is 2.1 square, that is 4.41. Now the ratio of C minimum to C maximum is 4.41. Correct answer is option 3. Image frequency is 1600 kilohertz and the ratio of C minimum to C maximum is 4.41. Next question, in a series RLC resonance circuit at half power points. So the image shows series RLC circuit frequency response characteristics. Here FR is a resonant frequency, F2 is higher cutoff frequency, F1 is lower cutoff frequency. At higher cutoff frequency and at lower cutoff frequency, the magnitude is 0.70 times of maximum value or 1 by root 2 times of maximum magnitude, and the power is half of the maximum power. Power is half of the maximum power. At cutoff frequencies, voltage is 1 by root 2 times of maximum voltage, current is 1 by root 2 times of maximum current, and the power is 1 by 2 times or half of maximum power. So we know that in series RLC circuit at resonance reactance is 0. So reactance is 0 means the total impedance is equal to resistance. So Z is equal to R. In series RLC circuit at half power points resistance is equal to reactance. Resistance is equal to reactance. Then impedance Z is equal to R plus or minus J R, because both the value of resistance and reactance are same at half power points. Then total impedance Z is root 2 R. So total impedance Z is root 2 R. At half power points, the magnitude of impedance is root 2 times of impedance at the resonance. So this is the at resonance total impedance Z is equal to R, that is resistance. At half power points impedance Z is root 2 times of resistance. Correct answer is the resistance is equal to resultant reactance. So resistance is equal to resultant reactance. In series RLC circuit at half power points both resistance and reactance are same. Question number 12. If the transmission bandwidth is doubled in frequency modulation, signal to noise ratio is, in frequency modulation output signal to noise ratio is proportional to square of bandwidth, approximate case. So here bandwidth is doubled 2BW, then new signal to noise ratio increases by 4 times. Signal to noise ratio increases by 4 times. Correct answer is option 4. Question number 13. The transfer function of electrical low pass RC network. So this is a low pass RC network. It consists of resistor and capacitor. For a low pass filter, output is taken at the across the capacitor and resistor is connected to input side. Va of t is the input voltage, V naught of t is the output voltage. Let I of t be the current flowing through the circuit. The same circuit can be represented in frequency domain. Vi of t is represented as Vi of s, I of t is represented as I of s, current flowing through the circuit. Resistance is same as R. The capacitor in S domain is 1 by SC. Output voltage V naught of t is V naught of S. These are time domain representation and frequency domain representation for low pass RC low pass filter. Now the transfer function is, in the question they need to calculate the transfer function. So transfer function is ratio of output to input V naught of S by Vi of S. So V naught of S is voltage across the capacitor, that is I of S into 1 by SC. And the input voltage Vi of S is R plus 1 by SC into I of S. So this 1 by SC, I of S and I of S get cancelled. Now V naught of S by Vi of S is 1 by SC by R plus 1 by SC. On rearranging, we will get V naught of S by Vi of S is equal to 1 by 1 plus S R C. So correct answer is option 1. Question number 14. Voltage divider bias. So in voltage divider bias, this question is related to stability. The stability factor of voltage divider bias S is equal to 1 plus beta by 1 plus beta into Re by Re plus Rb. Now if Rb by Re tends to infinity, so this expression can be rearranged as 1 plus beta by 1 plus beta, take Re common, 1 by 1 plus Rb by Re. If Rb by Re tends to infinity, so if this value is infinity, now we will get stability factor S is equal to 1 plus beta. If Rb by Re tends to 0, then stability factor S is equal to 1. In voltage divider bias is essentially independent of beta if Rb by Re tends to 0. If Rb by Re is 0, then stability factor is S is equal to 1. It is independent of DC current gain beta. Independent of current gain beta. So voltage divider bias cannot be independent of beta DC. So it is wrong. It can be independent of beta when Rb by Re tends to 0. It can be essentially independent. So option 2 is correct. This voltage divider bias is not widely used. Option 3 is incorrect because it is widely used. This voltage divider bias is widely used. It requires fewer components than all other methods. So it is also incorrect. It requires more number of components. Voltage divider bias requires more number of components when compared to other biasing techniques. Correct answer is option 2. Next question. A pole zero plot of open loop transfer function system shown below and the steady state gain is 2. The transfer function of the system is given as. So from the given graph, from the given plot, the pole locations are at S is equal to minus 2 plus j and S is equal to minus 2 minus j. These are the pole locations S1 and S2. Next, zero location is at minus 1. The pole locations are minus 2 plus j, minus 2 minus j, and 0 location is at S is equal to minus 1. So from this, transfer function is k into S plus 1 by S plus 2 minus j, S plus 2 plus j. So from this, transfer function is k into S plus 1 by S square plus 4s plus 5. Also given the steady state gain is 2. So limit s tends to 0 into transfer function is equal to 2. So on substitution, we will get the value of k is 10. Therefore, final transfer function is k into S plus 1 divided by S square plus 4s plus 5. So 10 into S plus 1 by S square plus 4s plus 5. This is the correct answer. Option 1. Question number 16. If C is noise channel capacity bits per second, delta F is bandwidth in hertz, and signal to noise ratio is S by N. Then what is the formula for channel capacity? We know that channel capacity C is equal to B into log to 1 plus signal to noise ratio bits per second. In the question, bandwidth is represented as delta F. The channel capacity C is equal to delta F into log to 1 plus signal to noise ratio bits per second. Correct answer is option 2. Question number 17. For a reverse biased PN junction, the current through the junction increases abruptly at. So obviously the answer is at breakdown voltage. In the reverse biased PN junction, the current increases abruptly. This is because the strong electric field at the junction can cause electrons to be pulled from their covalent bonds, creating a sudden surge in current, sudden increase in the current. Correct answer is option 1. In a reverse biased PN junction, the current through the junction increases suddenly at breakdown voltage. Question number 18. A forcing function t square minus 2t into u of t minus 1 is applied to a linear system. The Laplace transform of the forcing function is. So given function f of t is t square minus 2t u of t minus 1. So we know that Laplace transform of t power n is n factorial by s power n plus 1, and shifting property Laplace transform of x of t minus t naught is e power minus s t naught x of s. Using these two formulas, we will solve the given forcing function to find the Laplace transform. F of t is t square minus t 2t u of t minus 1. So it can be rewritten as f of t is equal to t minus 1 whole square u of t minus 1 minus 1 into u of t minus 1. Now apply these two formula. T minus 1 whole square, that is t square is 2 factorial by s cube e power minus st naught, that is e power minus s into 1 minus Laplace transform of 1 is 1 by s e power minus s into 1. So that is 2 by s cube e power minus s minus 1 by s e power minus s. 2 minus s square by s cube into e power minus s. So correct answer is option 4. Question number 19. The signal transmission in optical fiber communication systems takes place through the dash modes only. In optical fiber, there are three modes of propagation. One is guided mode, leaky modes, and radiation modes. So guided modes are those that are confined to the waveguide structure, propagating without significant loss of energy, and these guided modes are used for communication. Correct answer is option 3. Leaky modes are partially guided but also radiate energy. Attenuation exists and it is not suitable for communication. So attenuation exists in these leaky modes, not suitable for communication. Radiation modes, these radiation modes are unbounded modes that are not confined within the waveguide structure, fiber optic structure. Radiation modes causes signal losses. So this leaky mode not useful, radiation mode not useful, and the only mode that is used for communication is guided mode. Next question. Identify the incorrect statement. Both preset and clear inputs should not be active simultaneously. So this statement is correct. Both the preset and clear inputs should not be active simultaneously. So in the question they asked identify the incorrect statement. So statement A is correct. Next one. When the preset input of flip-flop is active, it sets the flip-flop to logic 1 irrespective of state of asynchronous input. So the statement 2 is also correct. When the preset input is active, it sets the flip-flop to logic 1 irrespective of state of asynchronous input. Statement 2 is also correct. Statement 3. In JK flip-flop with active low JK inputs will function like a toggle flip-flop for j is equal to 0, k is equal to 0. So here toggling takes place for j is 0, k is 0 because flip-flop is having active low inputs. For active high jk input, flip-flop will toggle for j is equal to 1, k is equal to 1. Statement 4 is also correct. In the question they asked to identify the incorrect statement. So D flip-flop is same as D latch. So this statement is incorrect. It is a correct answer. So let us see. When preset input is activated, the flip-flop will set regardless of any synchronous input or clock. When clear input is activated, the flip-flop is reset. When preset input is activated, flip-flop is set. When clear input is activated, flip-flop will be reset. Both preset and clear, asynchronous or direct inputs should not active simultaneously. Next statement, a JK flip-flop with active low J inputs will toggle for J is equal to 0, K is equal to 0. A JK flip-flop with active high inputs will toggle for J is equal to 1, K is equal to 1. Next, D flip-flop and D latch both are not same. D flip-flop and D latch both are not same because in D flip-flop, change of output for a given input takes place only when clock signal is applied, whereas in D latch, change in output changes takes place instantaneously. So correct answer is option 3, which is the incorrect answer. D flip-flop is not same as D latch. Next question. An RC network has a capacitor of 2 microfarad with resistor of 1 mega ohm. The time of 6 seconds is equal to, given in an RC network with resistance 1 mega ohm, capacitance 2 microfarad. Now the time constant of the circuit is tau is equal to RC. The formula for time constant tau is equal to RC. So RC is 2 seconds, but in the question they have mentioned 6 seconds. Now 6 seconds is equal to 3 times of time constant, 3 tau. Correct answer is option 3. Next, all zeros of transfer function lie in the left side of the S plane. Then the system is, so it is minimum phase system. So minimum phase system have all poles and zeros in the left half of the S plane. For non-minimum phase system, one or more zeros exist in the right side of the S plane. All zeros of transfer function lie in the left side of the S plane, then the system is minimum phase system. Let us see definitions here. An all-pass system is a signal processing system that has constant magnitude response across all frequencies, meaning it doesn't change the amplitude of the input signal, but it can alter its phase. Only phase is changed, but not the altitude. It is crucial concept in signal processing, particularly in designing filters and equalizers. All-pass system is characterized by having poles and zeros in conjugate reciprocal pairs in the complex plane. So it is characterized by having poles and zeros in conjugate reciprocal pairs in a complex plane. Next is minimum phase system, a system where all poles and zeros of its transfer function are located inside the unit circle or in the left half of the S plane. For a non-minimum phase system, it is a system where some of its zeros are located in right half of the complex plane. Non-minimum phase system poles and zeros may lie on the right half of the S plane. So correct answer here is minimum phase system, because in the question all zeros lying on the left hand side of S plane. Question number 23. In what type of multiplexing does each signal occupy the article entire bandwidth of the channel? So obviously it is time division multiplexing. In time division multiplexing, entire bandwidth is allocated to the user for a unique time slot for their operation. Entire bandwidth is allocated for the user for a particular time slot. So it is time division multiplexing. Whereas in case of frequency division multiplexing, fixed portion of available bandwidth is allocated to the user for an entire time duration. In FDM is an analog technique. This frequency division multiplexing is an analog technique, whereas TDM, time division multiplexing, is an digital technology. In TDM, users allocated to use total available bandwidth on time sharing basis. Total available bandwidth on time sharing basis. Correct answer is for TDM. Question number 24. How many op amps based voltage comparators are used in 555 timer IC. So obviously the 555 timer IC consists of two comparators, upper comparator and lower comparator. This is an upper comparator and lower comparator made with operational amplifiers, and three internal 5 kilo ohm resistors acting as a voltage divider, providing a bias of 2 by 3 VCC to upper comparator and 1 by 3 VCC to the lower comparator. It consists of POS transistor, SR flip flop, inverter. So correct answer is option 3. The number of op amps used in 555 timer is 2. Question number 25. What is the value of RB and RC in the circuit given below? If the data as follows: ICQ, quiescent collector current, ICQ is quiescent collector current, and it is given as 1 milliampere. RC is a collector resistance, RB is a base resistance, and VCC biasing voltage, VCC is 10 volts, DC current gain beta is 100, VCEQ, quiescent collector emitter voltage, which is 16 volts. So this is a given data. We know the relation that IC is equal to beta IB, since it is an common emitter configuration. So the circuit given is common emitter configuration. Emitter is connected to ground. Here it is collector terminal, base terminal. Base current is IB, collector current is IC. The resistor connected to base is base resistor. The resistor connected to collector is collector resistor. Output is taken across the collector and input is given across a base. Emitter is grounded. IC is equal to beta IB. So IC is given. Collector current is 1 milliampere, 10 power minus 3. Beta is 100 and the base current. So therefore base current is 10 microampere. In a transistor, the relation between the currents is emitter current is equal to base current plus collector current. So we know collector current and base current. Collector current is 1 milliampere, that is 1000 microampere plus 10 microampere, 1010 microampere, that is 1.01 milliampere. This is the emitter current. Now write the KVL at the input side. VCC is equal to, this supply voltage VCC is equal to IBRB plus VBE. IBRB plus VBE. So VCC is bias voltage, which is 10 volts, minus IB is 10 microampere, 10 into 10 power minus 6 into base resistance RB, minus VBE, base emitter voltage. So this base emitter voltage is 0.7 volts, 0.7, it is equal to 0. Now base resistance RB is equal to 10 minus 0.7 by 10 power minus 6. Its value is 0.93 mega ohms. Similarly, write KVL at output side. VCC is equal to ICRC plus VCE. So VCC is 10 volts, IC collector current, IC is equal to 10 power minus 3 into collector resistance RC plus VCE. VCE value is 6 volts. So that is 10 minus 6 by 10 power minus 3 into RC. Now RC is 4 kilo ohms. So correct answer is option 2, 0.93 mega ohms, 4 kilo ohms. Question number 26. An air-filled rectangular waveguide has dimensions of 2 centimeter and 1 centimeter. The range of frequencies over which the guide will operate single mode TE10 mode of operation is given. So in the question they have given air filled waveguide with dimensions 2 centimeter by 1 centimeter. And the given mode is TE10 mode. For TE10 mode is m is equal to 1, n is equal to 0. The cutoff wavelength lambda 1 is 2a, because TE10 is a fundamental mode or dominant mode. 2 into a, that is 2 into 2 centimeter. So lambda 1 is 4 centimeter. So now cutoff frequency FC1, we need to calculate the range of frequencies. So the range of frequencies. Now FC1 is C by lambda 1, 3 into 10 power 4, 10 power 8 by lambda 1 is 4 centimeter. 1 centimeter is 0.01, 10 power minus 2. Its value is 3 by 4, that is 7.5 gigahertz. Now the second wavelength lambda 2 is 2b, where b is 1 centimeter. So 2b is 2 centimeter. Cutoff frequency FC2 is 3 into 10 power 8 by 2 into 10 power minus 2. So it is 15 gigahertz. Now the range of frequencies is from 15 gigahertz and 7.5 gigahertz. So the range of frequencies over which the waveguide operate is 7.5 gigahertz to 15 gigahertz. So correct answer is option 3. Next question, in PCM for Q quantity levels, the number of pulses in code group is given by. So for n bit pulse code modulation, the number of for n bit pulse code modulation, the number of quantizer levels L is equal to 2 power n, step size delta is peak to peak voltage by 2 power n, quantization error is sampled value minus quantized value, maximum quantization error is plus half of step size or minus half of step size, and quantization error varies from minus delta by 2 to plus delta by 2. Bit duration TB is sampling period by number of bits per sample, and bit rate RB is n into sampling frequency. The number of pulses in code group is equal to log 2 number of quantized levels, that is log 2 Q. Quantized levels is represented as Q. So the correct answer is option 2. Question number 28. The resistivity of P region and N region of germanium diode are 6 centimeters and 4 ohm centimeter. So given the resistivity of N type region, rho n is 6 ohm centimeter, and the resistivity of P type region is 4 ohm centimeter. So once the resistivity is known, we need to calculate the conductivity. We know that conductivity sigma n is reciprocal of resistivity, that is 1 by 6 mho per centimeter. Its value is 0.160 mho per centimeter. Similarly, conductivity in p-type region is sigma p is 1 by rho p, that is 1 by 4, 0.25 mho per centimeter. Also given the mobility of hole mu n is 3800 centimeter square per second, mu p is 1800 centimeter square per volt second. Mobility of hole, mobility of electron is mu n 3800 centimeter square per volt second. Intrinsic carrier concentration is 2.5 into 10 power 13 per centimeter cube. Charge of electron is 1.6 into 10 power minus 19 coulomb. Thermal voltage Vt at 300 Kelvin is 0.026 volts or 26 millivolts. This is the data given in the given question, and they ask to calculate the contact potential V0 and potential energy barrier. So this is the data. So we know that sigma n is nq mu n, and the value of sigma n obtained is 0.160. So that is 0.160. Donor concentration, charge of electron is 1.6 into 10 power minus 19 coulomb, and the mobility of electron is 3800 centimeter square per volt second. 3800. Now we will get donor concentration. Nd is 2.741 into 10 power 14 per centimeter cube. Similarly, sigma p is 0.25. We need to calculate the P, that is acceptor concentration. Q is 1.6 into 10 power minus 19, that is charge. Mobility of hole is 1800 centimeter square by volt second. So from this, acceptor concentration is equal to 8.68 10 power 14 per centimeter cube. So these are donor concentration, acceptor concentration, and intrinsic concentration is 2.5 into 10 power 13 centimeter cube. Using these three, the contact potential V0 is equal to kT by Q ln of Na Nd by Ni square. So kT by Q is 26 millivolts as per the given question at 300 Kelvin. So now V0 is 0.1534 volts. The potential energy barrier is QV0 1.6 into 10 power minus 19 into 0.153. So potential energy barrier is 0.1534 electron volts. So it is in joules. So it is in electron volts. So correct answer is option 4, 0.1545 volts, and potential barrier is 0.1545 electron volts. Next question. A lossless air-filled dielectric cylindrical waveguide of inside diameter of 3 cm is operated at 14 GHz for TM11 mode propagating in plus z direction. The wave impedance is. So in the given question, the data given is air-filled cylindrical waveguide of diameter is 3 cm. Diameter d is 3 cm. So now the radius is half of the diameter, that is 0.03 by 2 meters, that is 0.015. Operating frequency is 14 GHz. Velocity of light we know that is 3 into 10 power 8 meters per second. So the intrinsic impedance of free space, that is air, is 377 ohm or 120 pi. Now for a cylindrical waveguide in TM11 mode, the cutoff frequency Fc is x11 into c by 2 pi a. This is a formula where x11 is 3.832 and c is a frequency Fc, that is 3.832 into 3 into 10 power 8 meters per second into 2 pi a. A is a radius, its value is 0.015. The frequency upon calculation we will get cutoff frequency Fc is 12.159 into 10 power 9 Hertz. And the wave impedance for TM11 mode. Wave impedance for TM11 mode ZTM is eta naught square root of 1 minus Fc by F whole square. Eta naught is 120 pi, that is 377 into 0.49. So it is approximately equal to 185 ohms. So correct answer is option 2. Next question. A MOSFET differs from JFET mainly because. So this JFET is operated only in depletion mode, whereas MOSFET is operated in both depletion and enhancement mode. Conductivity is controlled by reverse biasing of the gate. Here conductivity is controlled by the carriers induced in the channel in MOSFET. So input impedance of JFET is high. For MOSFET it is very high. So drain resistance is high. Here drain resistance is low. Manufacturing process of MOSFET is complex, whereas manufacturing process of JFET is simple. MOSFETs are more susceptible to damage, and these are less. JFET is less susceptible to damage. Less noise applications, mainly used in high noise applications. MOSFET is expensive. The gate leakage current of MOSFET is in the order of 10 power minus 12. Therefore, input impedance is very high. So MOSFET differs from JFET. MOSFET has two gates. It is wrong. MOSFET does not have physical channel. It is wrong. Because of power rating, no. JFET has PN junctions. Correct answer is option